new blockchain, and the new Genesis block is here. I would like to introduce Ittay Eyal, who's the professor in Technion. He's going to talk about trusted hardware meets blockchain.
Thank you. Thanks very much, Elaine. Yeah, so my name is Ittay. I'll talk today about how trusted execution environments, trusted hardware, helps in the context of a blockchain, what it can, what it cannot do. And I hope to raise some interesting questions, demonstrate them. So on the face of it, it seems that the two things are kind of unrelated. The blockchain gives us this decentralized, unpermissioned, replicated state machine that clients can interact with, forming this famous log. And they can also use smart contracts to form direct peer-to-peer interactions backed by the shared log, the blockchain. And at the same, in parallel, I don't know, the trusted execution environment lives on a completely different world, right? This is a guarantee you get from a single machine. Inside the single machine, you have this trusted element, and we have these implemented by Intel and ARM and AMD, and there are some more coming up. And what this gives us is the following. We have the trusted processor running on the machine, and we have some code plus data that we trust. We believe that this code does what we think it does, and we trust the manufacturer of the hardware. And we don't need to trust anything else. So even the operator of the machine can replace hardware that we don't need to trust. We don't need to trust even the memory on that machine. The operating system, maybe hypervisor, we don't need to trust them, or any other code that runs on that machine. And what the guarantee we get from the processor is confidentiality. So even the operator of the machine cannot see what's happening inside the code, and this includes a random number generator that we're going to use. The operator of the machine cannot affect the code even without seeing it. So this is integrity. And finally, we have remote attestation. This is critical. This is a remote attestation. So this is Alice's computer, and she runs the code on the trusted hardware. And she can send an attestation to Bob with the output from the execution of the command, a fingerprint of the code and data fed into the trusted processor, and the signature from Intel that this is the correct output of running this specific code on an Intel hardware. So if you trust Intel, then this is the correct output. You don't need to trust Alice or any of this. Which sounds pretty fantastic, right? So we know that blockchains have some issues on performance, security challenges, and of course the unbelievable waste of proof of work. So can trusted execution environments simply solve all of these issues? And to quote Betteridge's law, the answer is no. And the reason is that trusted execution environments, trusted hardware has limitations. So mostly they don't have any I/O. So any access to the outside world goes through the system operator, Alice. This means the hardware, the execution environment, cannot access the blockchain. It can ask Alice to put something on the blockchain, can ask Alice what's on the blockchain, but it cannot access it directly. Secondly, individual trusted execution environments can be compromised. Arguably, this is an expensive endeavor. You need electron microscope, and it's expensive, but in principle it is possible to see what's inside there. And finally, TE designs have vulnerabilities, as we've seen recently with foreshadow. So all Intel processors suddenly became vulnerable until Intel issued the fix. And we're not aware currently of any open vulnerability, but it may arise, and we need to keep it in mind. So with all of this in mind, I want to talk about two specific projects, and we'll see how they overcome these limitations, and some open questions that they demonstrate. One project works at the blockchain level. So we're trying to use TEs to improve on blockchain behavior, and another is improving on the second layer of payment channels. This is called TEEChain. I'll start with the first proof of useful work. So proof of work, as in Bitcoin, Ethereum, and friends, uses proof of work as follows. A block proves statistically some waste of resources in the real world. This is capital expenditure, buying hardware for doing proof of work, and operational expenditure, your day-to-day expenses in electricity, etc. And the point is that the attacker must waste a similar amount of resources in order to successfully attack the system. And arguably this is not waste. We're using these resources to secure the system, but we would like to do better. Right? We would like to get that security without wasting, without running all this useless computation. And there have been actually quite a few suggestions around. You could run a permission system. It's a different model, but it doesn't have the waste. You can do internal waste, proof of stake. Again, this makes different assumptions and produces different guarantees, but this is also an approach. There are useful resources, say calculate specific prime numbers or store some data and prove that you are storing it. There are two issues with this approach. First of all, some of these are, so for example, finding specific prime numbers is not generally agreed to be useful. And the worst issue, I guess, is that the useful resources are sometimes useful more to some people than to others. So if you or your organization thinks that this is useful, your utility is going to be different from running this than another organization that doesn't find the specific work to be useful. So only some people are going to mine and others are not. We're destroying the democratic and permissionless nature of the system. So when you introduce TEs into this picture, you're leaving, I guess, or moving into a model that we call partially decentralized. So we want guarantees that are similar to proof of work, and anyone can join. They go to the store and they buy an Intel processor and they can run SGX, for example. But we're adding a level of trust. We need to trust that the secure hardware manufacturer is following the rules. And indeed, Intel proposed to do something like this in what we call the partially decentralized model. They're saying instead of doing the cycles, running the work, do nothing. Just wait for an exponentially distributed amount of time, like it would happen to you with proof of work. And then your CPU will tell you if you generated a block or you did not. So this sounds great, like proof of work, like guarantees, but energy, no waste of energy. But there are two issues. So the first one is what we call the stale chips problem. The thing with waiting is that you could wait with an old, cheap CPU just as efficiently as you wait with a new cutting-edge CPU. So our analysis shows that the Nash equilibrium, epsilon Nash, in this world is that you're going to build these farms with old CPUs, and you're going to waste the same amount of effort. Instead of on power, you'll waste it on hardware. Yeah.
Is the relation, or should I think of it as proof of stake, where my stake is the CPUs?
I don't think this is equivalent to proof of stake, because when you're using CPUs in this way, you are tying the CPU to a specific block for mining. This is kind of similar to what happens with proof of work. So you cannot use the same CPU to mine on two different blocks at the same time. Technically, this actually requires some effort, but this can be enforced. Whereas with proof of stake, in principle, if you do a naive design, you have what's known as the what's at stake problem, right? You can mine on any number of blocks at the same time because you have stake on all branches. Yeah.
I was going to say this is just proof of CPU.
Right. This is proof of CPU.
So did this analysis take into account that now you're going to increase the value of older CPUs?
We have not, with state of mind that the old CPU market is significantly larger than what we expect to be run here. But this is, I mean, at some point we had to make this choice, right? Yeah. So the second problem is what we call the broken chips problem. I said earlier, individual chips can in principle be compromised. And a chip that is compromised in this way can generate as much so-called proof of work or proof of weight as the operator wants. And the solution Intel proposed was statistic. What we also wanted to look at is the adversary's advantage when doing this and the cost of this test. And I'll elaborate on this later after I'll present our solution. So what we presented was something we called resource efficient mining using proof of useful work. This is joint work with Fen Zheng, Robert Escriva, Ari Jules, and Robert Van Renesse from Cornell. So the idea is the following. We're going to dedicate not the CPUs themselves, but the work run on them for mining. So we're actually going to take the work and use it for the proof of work, but the work is going to be work that we choose. So think of it as you're running your own workload. So you're optimizing for machine learning, you're looking for a cure for cancer, you're running some simulations, doesn't matter, whatever you do in your lab. And you associate this work for mining. This is the goal. And the challenging question is how to measure and prove this and enforce the association of the work. What we want is the following. We need a memoryless random distribution. That's the interval or the time it takes you to find a solution. We need the difficulty to be tunable. These are really just the Bitcoin, Ethereum properties, right? Standard properties. We need O of 1 validation, right? Validating the blockchain should be quick. And all the data has to be on the blockchain. That is, we cannot have, so you're running your workload for machine learning, you can't expect a validator to access this private data in order to validate the blockchain. It has to be small and inside the blockchain. And this is the outline of the solution we propose. So all of this is run inside what Intel calls the enclave. This is the secure code, the trusted code. You feed into it the useful work that you need, the task that you need to perform, and the header of the block that you're mining on. And this is, the CPU is going to run this code, and whenever there's useful output for your useful work, you're going to get that useful output directly. And it also is going to count the instructions that the useful work is performing. And for every n instructions, it's going to explicitly simulate n separate Bernoulli tests. So just like it would do with the hash function in standard cryptocurrency. And if at least one of these is successful, then you get a block. So the enclave will spit out a proof of useful work. This will mean success. Yes.
SGX anyway, why just use it for only leader election and not running the entire protocol? That way you can just reduce visiting faults to omission faults, and then you can probably have a better construction.
I think this is what we're doing, right? This is only done for the leader election, but in a permissionless or semi-permissionless form. So you can join. So if the system works like this, you can join today. You don't need a permission system. Everything is run. I'll talk about the architecture very briefly later. But you have your blockchain client running separately, and this only does the proof of work. So you don't need to feed all the blockchain logic into this.
How are these permissionless? Every new user needs to have its enclave attested, right, to the other enclaves, no?
Right. So let's see what we actually need. This is an excellent build-up. So the output that we get from here is the proof of useful work. So this should really be an attestation that the enclave was run, that it's simulated with its internal random engine, pseudo random engine. It simulated the Bernoulli tests, and one of them won, and that gives you the proof of work. So this output is really an attestation. Now you should say, but you're lying. You told us that we can run anywhere, and if we have Alice, Bob, and Carol, each of them have their own useful work that they're performing, right? They are doing different things, and so this output is for a specific fingerprint. So do we need to feed all those fingerprints into the hard code them into the blockchain? That would defeat our purpose, right? We are hard coding the types of work that are parsable by the blockchain, and so only these types of work will be applied. And what we propose to do is form this hierarchical attestation. And the hierarchical attestation works as follows. So we're not authorizing specific fingerprints. We're authorizing fingerprints of instrumented code. So each of the participants takes their code, their useful work code, and put them through an instrumentation toolchain. And they get an enclave to execute. Now we take this enclave and we put it into our compliance checker, and the compliance checker makes sure that you are, and there are complexities there, but it makes sure that you're counting correctly, you're not cheating in the count, and that you're reporting correctly. This is done with a runtime, that you're reporting correctly the number, the instruction count. And it outputs, this is signed, this fingerprint is indeed a correctly instrumented enclave. And now your proof of work is actually two things. And that's the only two things you're going to need. It's the compliance checker attestation that your code is okay, and the enclave's attestation that you really did the work for the specific block. So this is our tool chain. I'm not going to go through it at all. Just at the end here, this is the point. So the compliance checker spits out the proof of compliance for this. And from this, you get the useful work and also proof of useful work if you're so lucky. And these two together go to the blockchain. These are not large data structures.
Can't now Intel own all the money in the world?
Again, please?
Can't Intel now own all the money?
Yes. Yes. That's an excellent point. So whoever manufactures the hardware can now produce all the as many attestations as they like. This is why we actually need Intel. So Intel's cycle over the year make this negligible. It's not worthwhile for such a large manufacturer to cheat on this. If you have a small startup that is securing a blockchain of billions, not good. Tempting.
There is some work that you not useful because there's an inefficiency when you run your useful work inside an enclave and not.
It's like an invited question. Perfect. Thank you. This is our overhead. So we get some overhead from, so in white it's native, it's always 1, and then you see our overhead, this light blue is for the SGX overhead, so just running the code inside an enclave without any instrumentation, and then the dark blue is the added
Can my code
overhead.
have IO?
Sorry?
The useful work can have the IO?
No, it's just, it's a batch. Right, right. And this is the reason, for example, the SVM has a high workload, because in the SVM, you see just from the SGX, you have to enter and leave SGX mode a lot of times, and that's why you get worse overhead. So between 5 and 15, we think this is much better than 100% waste. Yeah. Yep.
Was speculative execution-based side channels, which are basically subverting a remote attestation. So do you have any defenses for those? And if not, would they just completely subvert the security of your system?
So side channel. Okay, so side channels, as demonstrated in recent attacks and famously known, and even Intel say attest in their own texts that SGX in and of itself isn't protecting you against side channels. So if you can use the side channels to get the enclave signing key, essentially break entirely the SGX, then the system is broken. But if you only have visibility into what's running, you cannot affect, in principle, you cannot affect the code. So you will be able to see that you'll need so many, you'll be able to see, I guess, before the SGX tells you whether or not you won the block. But you won't be able to affect your chances. We only roll the dice at the end after we know how many instructions were counted.
So you rely on SGX for integrity and not confidentiality?
Yeah. Yeah, there are no secrets apart from the random number. This, by the way, is another difference from Intel's proof of elapsed time, because there you have to roll the dice at the beginning, and it tells you you have 1 hour until your block. And there, if you have visibility inside the SGX and you don't like that number, you can terminate it and start again.
Is it possible to distribute the trust for integrity in some way? So that if one enclave is attacked with speculative-based execution, then others, hopefully in other clouds, won't work.
Yeah, that's an interesting point. We have not done this here at all. Maybe we'll keep it for an offline discussion, but I'll talk a little bit about this later on in another context. Okay. Very briefly about the broken chip problem. So say you got that expensive Microsoft and you compromised your own chip, and now you're able to attest to anything. So you're not able to create many fake chips. Only Intel will be able to do that. But you'll be able to create as many attestations as you like for blocks without doing any work. So what we did is we created a statistical likelihood test that rejects blocks from the same CPU if they come at too high frequency. So if you're trying to produce blocks at too high frequency, your blocks will get rejected. If we're too permissive, the attacker gains, right? If we are not being strict, the attacker can make many blocks and make a lot more money than they're supposed to. If we're too restrictive, it means that, there's always some chance that someone might get lucky. So if we're too restrictive, we're causing them to lose money. And more importantly, we're reducing the security of the system because you're just throwing down the drain good work. So here's our analysis. We see this is a simulation run over the course of simulating a course of 60 days. And you see here in red the advantage of the attacker. This is how many more blocks in percent they're able to create over time. In the beginning, our statistical test is not very reliable because it doesn't have enough data, and so we're allowing a lot more blocks than we would have liked to. But over time, it goes down towards 1 and is able to correctly reject blocks, which means that it's not worthwhile for you to spend all this money on the microscope. Over time, it won't be worth it. You'll get only a few more blocks, and this is the inverse of that, how much work is wasted with the same statistical test. So again, we're looking at how many blocks we're rejecting because someone got too lucky. Initially, the statistical test is not very accurate, but over time, we're rejecting blocks very infrequently. We have a long-term statistic.
Can I ask you a question? So when you are beginning at day 0, you don't have any data yet, so you should not be rejecting too many blocks. then it should catch up, you should reject, and then it should stabilize. Why is this line like this? This blue line.
The blue line is the aggregate number of rejected blocks.
Yes, but shouldn't it start slow and then accelerate a little bit and then slow down again?
Perhaps we could have used a different statistical test. The one we used for the one we used, it was a bit too restrictive in the beginning, I guess. It's a good point. Yeah, so I guess my bottom line here is that using SGXs for for securing an actual blockchain is a delicate issue, and it only applies in specific contexts. So not for your general public cryptocurrency, for example. And it's too dangerous. There's also the issue of a wide compromise like the one we've seen recently for Intel. This, I believe, is a more practical context, which is payment channels among users of the blockchain. So this is the story of payment channels. You all heard this. So each user of the blockchain places a deposit transaction on the blockchain, and then they are able to pay one another directly, and each can unilaterally terminate the channel. They're done, place a transaction on the blockchain that gives them whatever they're owed. The basic structure for a unidirectional channel is the following. We have Alice paying Bob. Alice places the setup transaction. Everything below the blue line is on the blockchain. Everything above the blue line is not on the blockchain, but can be placed on the blockchain if there are sufficiently many signatures. So Alice gets this refund transaction that is time locked. After, say, 1 month, if Bob disappears, she can place it on the blockchain and get her money. This is not the desired scenario. What we're trying to do is a payment channel. So with the payment channel, what happens is that, say, Alice wants to pay $3 to Bob. She creates this transaction that pays Bob $3 out of her deposit of $100 and sends the 97 back to Alice. This requires 2 signatures from Alice and from Bob. Alice only gives her own signature on that, and Bob, if he chooses to spend this, to terminate, to settle the channel at this stage, can add his signature and place this on the blockchain. But we keep the channel open, and then Alice wants to pay $2 more to Bob, so she creates a new updated settlement transaction, again signed only by herself, and Bob can settle this. Now he gets 5, 3 plus 2, and Alice gets back 95. Alice cannot place this old transaction back on the chain because she doesn't have Bob's signature, and Bob will naturally choose the latest transaction because it gives him the most money. This is the settlement. So now we're interested in doing a bidirectional channel. Each party should be able to settle the channel at any time, but a party cannot roll the channel back. So Alice cannot pay Bob and then settle the channel at the state before she paid Bob. So here's a naive solution to do that. Just 2 unidirectional channels. Each of them place a deposit and they pay one another. We have a bidirectional channel, only it's not terribly efficient. See here, Alice paid Bob 100 and Bob pays back 50. Now Alice is supposed to be able to pay more to Bob, but she cannot because she depleted her channel. So this is not what we want. We'll have to go back to the blockchain and start a new unidirectional channel. This is not what we're looking after. And so there is a solution to that without trusted execution environment. The most famous instantiation of it is the Lightning Network, proposed by Poon and Drija back in 2016. And the idea of this and most other similar solutions is to do state updates. So what's a payment in this world? A payment is a capability of the receiver to close the channel or settle the channel at the current state. And also it is a capability to take all the money, penalize the other party if they try to settle at an older state. Okay, so when I receive the money, I get these 2 capabilities. But there's a catch, right? How do we do this? So this is easy. This is a signed transaction settling the current state, right? They produce it together with the signatures. But how do we do this? So I also, when I receive the money, I also get a secret. And the secret will nullify a deprecated settlement from the other side. So Bob gets a secret from Alice, and he can use this secret if Alice tries to settle an older state on the blockchain, which means that actually this one is abortable with a secret. So Bob gets a signed transaction settling the current state that is abortable with a secret. And the catch of all these solutions is that they require, so there's a lot of work on such channels and state channels and generalization of this, but generally this is the idea. And all of these solutions require real-time blockchain access, right? If we want to be able to abort a transaction, it means that once the transaction is placed on the blockchain, there is a time interval, and during this time interval, the transaction can be aborted, and after this time interval, the transaction cannot be aborted. Only blockchains are not real-time, right? And we have a demonstration from Bitcoin. This is the time it takes to place a transaction on the Bitcoin network over a few months, and you see that the confirmation time has even reached days. So we cannot honestly rely on a time-limited settlement requirement. We can, I mean, it becomes a very practical discussion, right? We can make the intervals very long, and then we have issue of locked-in funds until the time has passed. Yeah.
It's not necessarily an argument, but I don't understand why your graph goes beyond like 6 blocks.
Sorry?
Why does your graph goes beyond like, I know, 2 hours?
This is the time it takes for you to place a transaction on the blockchain. So someone issued a transaction, it goes into the peer-to-peer network, and it is not placed on the blockchain because the blockchain is full. It waits in line. And it waits in line between an hour and many hours. So this is not the time for a block to be buried inside the chain. That's about 1 hour always.
Some transactions did get through in
Right.
less time.
Right. This is average. This is average confirmation time, I believe. Yeah. So between the time they were placed and the time, yeah. So our goal is to avoid this real-time requirement using trusted execution environments, and we're going to get some additional benefits. So let's take off the. This is joint work with Josh Lin, Florian Kelbert, and Peter Pizzuk at Imperial College London. My student Oded Naor at the Technion, and Emin Gunsir at Cornell. Josh will present this in SOSP next week. So first of all, let's take the Strawman story off the table. The trusted execution environment is not a trusted third party, right? If we had a trusted third party, Alice and Bob would just give them, the trusted third party, their funds, and the trusted third party would take care of everything. But this is not the story of the third party. This is the story of the third party. There is some Carol sitting between Alice and Bob and the trusted execution environment, and Carol can say, okay, I'm holding your funds until you pay me something, or it can crash and have a problem. So this is not a viable solution. Instead, what we propose is the following structure. So each of Alice and Bob has their own trusted execution environment managed separately, and they move their funds to the control of their TEs. So they pay their TEs, and the TEs control the funds of the channel completely. Now, what do the TEs actually give us here? They give us the guarantee that they will only create a settlement transaction once. This is the issue. This is what we needed. They will not create they will not give, Alice's TE will not give Alice a settlement for a deprecated state. So how do we achieve this? I'll first describe the protocol briefly and then talk about correctness, and then some performance. So the two TEs form a secure channel. This is a bit more elaborate than the SOSP version. They create a direct channel between one another through their operators, Alice and Bob. So they really do a Diffie-Hellman handshake terminated inside the TE, using attestations that are validated inside the TE. So the process is following. First of all, they need to deposit some money into the blockchain, right? So Alice pays her TE, right? This is money that goes from Alice to her TE, and she has multiple such deposits. Now, she tells her TE, this is my deposit, and it's all the blockchain. Note that the TE cannot validate this, right? The TE doesn't have direct access to the blockchain, doesn't know. But we don't need that, that's fine. Now, Alice and Bob decide to open a channel. Let's call it the red channel. They do this handshake story. And then Alice instructs her TE to produce a message to Bob saying these are the transactions that belong to me. Now, Bob receives these. He gets the guarantee from the TE that these funds are really secure by keys that are inside the TE. And Bob can go to the blockchain and see that they really are on the blockchain. And he's motivated to do that because it's his money at stake. That is going to be at stake. And this, and now this deposit is associated to this channel, and the TE will not allow Alice to use this deposit for anything else, let alone take it out. Now, when Alice wants to do a payment, and this is a state with multiple associated deposits, Alice just needs to send a single message to Bob, a payment message. Bob sees this payment message sent from the TE, and now this message is the guarantee that the TE will not generate a settlement for an older state. That's all that he needs. There is no time sensitivity. On settlement, each TE produces the transaction to take money of all relevant deposits to both sides. It's quite simple, and then it stops. It will not produce another settlement. And interestingly, we can do something that we could not do before. The deposits are not locked into the channel ad infinitum, but only if they're necessary. So if Alice had the deposit A3 associated with the red channel, and then she doesn't need it because Bob paid more than she did, she can dissociate the deposit from the channel. This is a process she's doing with Bob. She needs Bob permission that he doesn't need this deposit anymore, and if he fails, then she can always settle the channel at the previous state. But otherwise, if everything went well, then she can now take this deposit and use it elsewhere. This is important. This is less transactions going to the blockchain. So now, importantly, once the once the deposits are on the blockchain, we don't need any blockchain access in order to form a channel, perform payments, and even release deposits if we're balanced out. So everything is very quick. This is instant payment in the sense that we don't need blockchain access. We're only limited by the latency between the two parties. Now let's talk about correctness. The first task is, of course, to define what we mean by correctness. So first we define perceived balance. Perceived balance is what each party thinks they have. It's their initial balance plus whatever they got minus whatever they paid. We also define blockchain balance. This is the balance that the blockchain believes each party has. The blockchain is its own entity. And for correctness, we want the user to be able to move her perceived balance to the blockchain. This is not done terribly formally here, but the details are in the paper. Our proof is simulation-based. So we're using TE and blockchain as ideal functionalities, and we create this functionality of the TEEchain. And then we show that the TEEchain actually maintains the blockchain and channel balances. And the ideal world execution are indistinguishable from the real world. So in the interest of time, I think I'm going to skip this element and assume we already have this TEEChain ideal functionality. We want to show, again, that each party is able to receive what she should have on the blockchain. So we do this constructively. We write down this, this algorithm that takes the money off all channels. This is a bit tedious, but it works out. So it settles all the channels depending on what state each channel was, and then moves it back into the blockchain outside the deposits. So we first prove that the protocol indeed completes. Specifically, if Alice wants to do this, Bob cannot do any operation that would prevent Alice from completing the protocol one way or another. Then we show that the functionality maintains the invariance. The perceived balance of an entity equals her what we call actual balance. We define an actual balance that is the combination of her balance on the blockchain and her balance on the chain, on the payment channels. And then we show that after completion, the actual, which is actually also the perceived, is actually present on the blockchain. Now a few words about failures. So we trust that Intel is not going to risk their annual revenue for attacking the system, but this trusted execution environment has all our money inside it, and if we run out of battery, there's a power failure, then we lose it all. This is not desirable. And the naive solution would be to do a backup, right? We ask the TE to produce this backup, we put it on our hard drive, and then if we lose power, we load it again. And if we do this naively, then this opens the door to a natural replay attack where the Alice pays Bob, generates a backup, pays Bob, shuts down her machine, bootstraps from the state before the payment, and goes to settle the channel and have the Lamborghini and her money as well. Instead, what we do is, I'll offer you two solutions to this. One is monotonic counters. So Intel provides in most of its motherboards the ability to use monotonic counters, meaning that there is a counter that is controlled, that is secured, controlled by the SGX that is only increasing. So we increment it on each backup, on each store of the state, and we only, and this incremental counter is maintained through reboots. And so if we reboot and the incremental counter, the monotonic counter is not where it should be, then we don't load it. This is mostly fine, only it's very slow. So the hardware only allows 10 of these every second. It takes 0.1 second to run this. And so this is good if I'm doing it from my laptop and I do a few payments a day. But if there are two exchanges that want to do frequent payments among one another for arbitrage or whatever, this is not an applicable solution, or they can take a risk, like a 100 millisecond risk. Yeah.
I worry that you can get in an inconsistent state where you incremented the counter but the state is old, or maybe the state is new but you did not increment the counter. So because it has to be an atomic operation, right? When you
right, you'll have
send things to storage, because otherwise it can be inconsistent. And there's a bunch of working space like that, Yadmin paper and so forth. I wonder why you didn't just use one of those rather than create your own solution.
That might have been before. I don't know. I don't know that line of work.
The line of work in the past few years at Unique Security Oakland.
Sorry.
There's a number of papers on this topic at Unique Security in Oakland in the past few years. One of them, for example, is Ariadne, and they're trying to. I mean, they're basically making SGX be able to, back up and prevent this kind of replay attacks.
Yeah, so I think that this is based on this approach. I don't think that there's anything particularly interesting here.
What about the atomicity of the operation?
Right, you have to allow for this one-off.
But then you can lose your money, right? There's a certain situation in which you can.
Yeah, you have a short interval, but that's not a lot of time. So you're reducing your risk.
So, like Ariadne, so.
I'll be glad to check this out. Yes. Thank you. So the solution that I think is actually more interesting is the following. This requires, admittedly, a lot more resources, though. What we do is we produce this chain of TEEs. So 3 TEEs running on separate machines with different failure modes. And each command goes through all the machines. So this is like a classical chain replication for storage, right? Only here, this is not about storage. We do want to keep the throughput, and we're giving up some latency like in storage. But here, in case of failure, we are doing something a bit different. So say we're running through these 3 TEs, and one of them or 2 of them fail. We have just 1 TE remaining. What we can do here, what we have to do here, is at this point settle the channel. So we replicate as much as we want for security, but once the chain breaks, we cannot allow for continued payments because that would allow for a clever attacker to chop it in a careful way and then let some portion advance in order to produce a payment and another remain in the old state in order to settle at a deprecated state. And so once one of them fails, we go back, we settle the channel at the state that is maintained in the CPU. This requires a lot more resources. So this is not for me running on my laptop. This is for the exchange scenario where the stakes are sufficiently high to justify running this in a geo-replicated way. So we actually tried this. We opened a channel between Imperial College London and Cornell, and we made some payments. We had either one backup or no backup. And this is the measurements we got from Lightning. So Lightning batches its transactions. So you have to, they accumulate, as you see here, over a certain time, and then they're placed in a transaction that is placed. We don't have to have batching, but we can. And you see the significant increase in throughput, mainly because we don't, in order to complete a payment, we don't need to do much more than just send a single message from one side to another. There is a significant overhead, as you see here, when we have to go across the Atlantic again for chain replication. So if we want this mechanism, right? Then we get a significantly higher latency. How am I on time?
10 minutes.
10 minutes? Perfect. So one last interesting point about all of this is multi-hop payments.
You actually hit -5.
You're actually 5 over.
You should have finished negative already.
Oh, and negative? Okay, I'm sorry. So I will not talk about multi-hop, but I'll be glad to tell you about it if you're interested. Demonstrates the curiosity of interaction between between trusted execution environments and blockchains. And since I'm out of time, I'm going to just leave this here, and thank you very much.
We will take over asking these questions.